Hello, and thank you for coming to my talk. I will be discussing the influences of mesoscale ocean eddies on flow vertical structure. And this work is part of the Ocean Transport and Energy Climate Process team, which is one focus of this session. To motivate this work, I'd like to first discuss the role of mesoscale eddies in the ocean energy cycle. This is a diagram of what the ocean energy cycle would look like in a model in which mesoscale eddies are resolved. So we have two energy reservoirs, potential and kinetic energy. These are maintained by buoyancy forcing and wind stress and can interact with each other through the overturning circulation and also through resolved mesoscale eddies. In reality, modern state-of-the-art GCMs are at best only marginally capturing mesoscale eddy effects. And so what this diagram looks like in a general circulation model is that there's this unresolved eddy kinetic energy reservoir, which is influencing both the resolved kinetic energy and the resolved potential energy. And of course, there's also dissipation pathways that would be missing from the model solution. One useful way of assessing to what extent a given model is resolving mesoscale eddies driven in particular by baroclinic instability is to consider to what extent the first baroclinic deformation radius is resolved. So here I'm showing the ratio of the deformation radius to the horizontal grid spacing for the 1/4 degree GFDL OM4 ocean model. So here a value of 2 indicates that there are 2 grid points per deformation radius. So anything within this isoline is considered eddy resolving and anything outside of that is considered non-eddy resolving. You can see that the majority of the domain here is not eddy resolving with the exception of the equatorial region. And this motivates the climate process team mission, which is to vet, improve, and unify new advances in energy, flow, and scale-aware eddy parameterizations, keeping in mind also that for the foreseeable future, our models will not be in the eddy resolving regime, and we have to deal with how to create scale-aware and physically motivated eddy parameterizations. The tool that we use for addressing some of these questions is an idealized model hierarchy that we refer to as Neverworld 2. This is a 1-basin stacked shallow water MOM6 configuration comprised of 15 isopycnal layers. There is zonal wind stress that is prescribed. The model is adiabatic, so this is the only mechanism by which it is forced. And here is the topography of the domain. So you can see that there is a topographic ridge that extends north-south through the entire domain. And there is a channel in the southern part of the domain that corresponds to the Antarctic circumpolar current. We consider 4 different resolutions. The lowest resolution is 1/4 degree and the highest resolution is 1/32 of a degree, and keep all of our model assumptions consistent throughout this suite of simulations, which really provides a nice test bed for parameterization development and for considering how resolution influences eddy effects. You can see by looking at the surface kinetic energy that there is a significant difference in the eddying character of the low resolution versus the high resolution simulation. And this is something that I'll discuss more throughout the talk. And also for reference, this is the same metric of the deformation radius to the horizontal grid spacing for the entire model hierarchy, which we consider here. One should keep in mind that in this set of baseline cases, we do not use any eddy parameterizations. So we can really consider how not resolving versus resolving eddies influences the flow. And so here you can see that the 1/4 degree case is roughly consistent with the OM4 plot that I showed earlier in terms of how well it is resolving eddies. Only the equatorial region has sufficient resolution of the deformation radius. As we move to the higher resolution cases, we see that by the 32nd of a degree case, we are now resolving the deformation radius throughout the entire domain. So the first thing that we can consider when understanding how the eddy resolution influences the resolved flow is to consider the kinetic energy and available potential energy of the large scale flow. So it's already well documented that increasing eddy resolution leads to decreased available potential energy and increased kinetic energy in a given model. So this is consistent with what we find in this model hierarchy. So here I'm showing the kinetic energy in APE, and you can see that for the 1/4 of a degree case, the kinetic energy is almost half that compared to the high resolution 32nd of a degree case. When we look at the available potential energy, it's a similar story that in the 1/4 of a degree case, we have the highest APE throughout the domain, and the APE decreases as we move to higher resolutions. However, there are many unknowns that kind of look more into the details of the energy structure. In particular, one unknown that I'll be focusing on here is what is the vertical structure of eddy energy in the ocean, both of the potential energy and kinetic energy. And also, how do mesoscale eddies shape the vertical structure and energetic pathways that the mean flow experiences? A useful metric to consider this is to perform a Baroclinic barotropic flow decomposition. So here I simply define a barotropic velocity as being the depth averaged velocity. And the Baroclinic velocity is the difference between the total velocity and the barotropic component. So the Baroclinic velocity is the part of the velocity that is variable with depth. From these two velocity components, we can compute kinetic energies, and we can look at the partitioning of the kinetic energy between the baroclinic and barotropic parts. And that is what I'm plotting as a zonal average and also 500-day average in these plots for the low resolution and high resolution case. One interesting feature stands out, which is that in the low resolution case, we can see that throughout most of the domain, with the exception of the ACC region in the south, most of the kinetic energy is in the baroclinic part of the flow. So more than 60%. When we move to the high resolution case, with the exception of the equatorial region, we see that the flow is now predominantly barotropic. So a great deal of barotropization has happened in the high resolution case, which is indicating that the vertical structure of the kinetic energy has drastically changed. We can also split these into mean and eddy components. And you can see that the main transition between the 1/4 of a degree case and the 32nd of a degree case is that now in the 32nd of a degree case, the mean flow is relatively weak. So it's only about 20% or less of the total kinetic energy. And the eddy component is really what's dominating, in particular, the barotropic eddy component. So this is indicating that mesoscale eddies barotropize the flow, but also we should keep in mind that the dynamical regime matters. So for example, in the ACC, where even at the 1/4 of a degree case, the flow is dominantly barotropic, this region is much less sensitive to enhanced resolution. So it's less important to resolve the deformation radius and these baroclinic instability length scales there. So now we will consider two regions in greater detail that have different dynamics. The first region is in the northwestern part of the domain, where the star is located. And in this region, the background flow is weak and somewhat baroclinic in nature. If we look at the 1/4 of a degree case, which is pictured in the top two plots, we can consider the time series of barotropic and baroclinic kinetic energy, similar to what I showed in the previous plot, but not as a time average now. So here you can see that there are strong fluctuations in time, and most of the fluctuations have significantly higher magnitudes of baroclinic kinetic energy. We can also look at the isopycnal fluctuations, which are an indicator of available potential energy of the flow. And so here I'm plotting isopycnal fluctuations in the vertical as a function of depth. So at each depth, how is the isopycnal moving up and down at that location? You can really see here that the isopycnal fluctuations are especially large near the surface. The green line here is showing the maximum isopycnal displacement over 500 days, and the purple envelope is showing the standard deviation over the same time period. When we look at the higher resolution case, we see that now there's a great deal more barotropic kinetic energy. Keep in mind also that the y-axis here is about an order of magnitude larger. The baroclinic kinetic energy is still substantial, but it is generally weaker than the barotropic component. If we look at the isopycnal fluctuations, we also see a profound shift in the vertical structure. Rather than being predominantly surface intensified, as in the low resolution case, we now see that the isopycnal fluctuations are strong, up to tens of meters at very deep parts of the domain. So here we see that eddies, resolving eddies really changes the vertical structure and leads to enhanced barotropization. The second case that we will consider is in the ACC, so at this location. And here, first of all, the energy is quite high compared to the previous plots. And also keep in mind the difference between the low resolution, high resolution y-axes. But in general, the interesting thing at this location is that the barotropic kinetic energy, again, is relatively significant, even at the low resolution case. And when we move to the high resolution case, the energy increases, but the vertical structure does not fundamentally change. This is also evident in the isopycnal fluctuations in the vertical structure of them. So we see that the isopycnal fluctuations do become larger as we increase resolution, but the vertical structure does not change as profoundly as in the previous case. So again, there's minor resolution dependence here. Eddies cause energy increase, but the vertical structure doesn't change. And we attribute this to the fact that the flow already is strong and barotropic. There are also standing meanders and barotropic eddies that are not driven by baroclinic instability in this region. And these processes are relatively well resolved. And so even at the quarter of a degree case, this allows the model to capture the correct vertical structure and the flow at this location. So one question that this leads to is what governs the barotropic baroclinic flow partitioning? Ultimately, this is an important process to understand because it can help us determine how to re-inject energy through backscatter in our eddy parameterizations. It can guide how the vertical structure of this backscatter is specified. So according to existing theories from the 1990s by Larachev and Held, this was for a two-layer quasi-geostrophic, relatively idealized system. The scale separation between the deformation radius, RD, and the energy containing scale, so this is the eddy scale, which we call RE, can help set the strength of the inverse cascade. So if we consider this as a ratio of the energy containing scale to the deformation scale, so RE over RD, the larger this ratio, the greater the extent of the inverse cascade. And so we can imagine that the greater this ratio, the more barotropization the flow can undergo. And so a greater amount of energy will end up in the barotropic component. So we tested this in Neverworld 2, and this is the result. So here I'm plotting the deformation radius in black, and then the energy containing scale according to two methods for computing this. In general, both of these methods rely on computing kinetic energy spectra, and then either looking at where the spectral peak is located, so this is the red line, or looking at where the centroid of the spectrum is, which is the blue line. Unfortunately, it's the domain of this simulation is not too large, and so in many situations, the spectra are computed as one-dimensional latitudinal spectra, and a lot of the energy tends to be at the largest resolvable scales. So sometimes it is really hard to gauge where the spectral peak is located. So there are some errors in this calculation, but nonetheless, if we look at the zonely averaged plot of what this looks like, here we're showing the barotropic baroclinic EKE ratio, and then this RE over RD ratio by these two methods. And we do indeed see a strong correlation between the separation between the energy containing scale, the deformation scale, and the barotropic baroclinic EKE partitioning. Some conclusions. Eddies influence the vertical structure by transferring momentum downwards and causing barotropization of the flow, and also increased fluctuations at depth. We also find that the change in vertical structure as a function of resolution depends on characteristics of the flow. So barotropic flow shows small sensitivity to resolution, and baroclinic flow shows a much stronger sensitivity to resolving mesoscale eddies and influencing the energy pathways. Here I'm just showing a summary plot of the fraction of barotropic kinetic energy in the low resolution, high resolution case. And again, you can see that the northern part of the domain where the flow is relatively weak has experienced the greatest change in the vertical structure. So some future work involves refining scaling theories for the barotropic baroclinic partitioning, in particular based on some recent work considering zonostrophic versus vortex regimes by Gaia and Ferrari. So we hope to better understand what sets this barotropic baroclinic partitioning and whether or not existing theories for two-layer quasi-geostrophic simulations can help us develop understanding in this regard. Also, we would like to test existing mesoscale eddy parameterization schemes, in particular focusing on those that include backscatter, where kinetic energy is reinjected into the resolved flow to mimic eddy effects, also within our idealized model setup. And finally, we would like to explore how the present results can guide vertical structure of energy that is backscattered to the resolved flow. Thank you for listening.